Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will see dimensions of physical quantity. In mechanics, generally basic three quantities are length, mass and time. So here length can be expressed in terms of capital L. Mass is expressed in terms of capital M and time is expressed in terms of capital T. And we always write dimension in square bracket. So the dimension of L will be in the square bracket like this. So first thing we will find out here dimensions of physical quantity, and first quantity we will consider, that is a length. So let us start from the length. What are the dimension of length? So we'll write here. So first physical quantity we will take length to find the dimension. So length, here we will take L, M, T. That is length, mass and time. In case of length, here we will write down power 1 because in length is present. But mass and time is absent, so we will write down power 0. Next physical quantity we will take, that is a mass. Again, the same way we will write, that is M, L, M and T. Here length is absent, so it's 0. Mass is there, so it is 1. And time is not there, so it is 0. The third physical quantity we will take, that is a time. In time, length is absent, so it will be power 0. Mass is also absent, so it is 0. And then time is present, so we'll take here power 1. So these are the three basic physical quantities. The next physical quantity we will take, that is the area. We know area is equal to length into breadth. Length and breadth both we can express in terms of L. So here we have L into L, which is equal to L square. Hence the dimension of area can be written as L raised to power 2. M, that is mass, is absent and time is also absent. And if you want to write down the unit, then from this we can write unit of area, that is meter square. Next physical quantity we will take for the dimension, that is a volume. We know volume, the formula of volume is length into breadth into height. So here all these three terms we can express in terms of length. So here we can write down length into length into length, that is equal to L cube. Now if you want to write down the dimension of volume, we will write down in a square bracket. So L raised to the power 3. Mass term is absent here, so we'll write down 0. Time is also absent, so we'll write down 0. And if you want to write down the unit of this, so L cube, L is nothing but length and that length is expressed in terms of meter. So the unit for this is meter cube. Next physical quantity we will take, that is a density. We know what is the formula of density. Density is nothing but mass per unit volume. So we'll write down here mass, that is M, and volume, we can express volume in terms of L cube. Hence dimension of density is L. But now L is in the denominator, so we'll write down here minus 3 raised to the power minus 3. The mass quantity is present there, so power of M is 1. But T is absent, time is absent, so we'll write down 0. If we want to write down the unit of density, from this we can write down. This is a mass. We know what is the unit of mass, that is kilogram. And this is length cube. Length cube is nothing but meter cube. So this will be the unit of the density. Next physical quantity we will take, that is a velocity. We know velocity is distance per unit time. So here we'll express distance in terms of meters. So here we have a quantity, that is a length, and time means here we have a t. So if you want to write down the dimensions, here dimensions are L1, t is in the denominator. So here mass is absent firstly, and t is in the denominator, so it is -1. And if you want to write down unit, the unit for this is length. L is length means meter, and time is second, so meter per second. Next physical quantity we will take, that is acceleration. We know acceleration is velocity per unit time. We can express velocity is distance per unit time upon time. So here we have a formula, that is a distance per unit time square. Now we can express distance in terms of L and time in terms of t. So here we have a t square. So if you want to write down dimensions, we will write down in this way. Firstly we will take a square bracket, then L1, power of L will be 1. Mass factor is absent here, so here we'll write down m0, and here t is in the denominator, so we'll write down here -2. This is the dimension of acceleration. If you want to write down unit, then here length can be expressed in terms of meters and time in terms of second, and here time square, so we'll write down a second square. This is the unit of acceleration, and this one is a dimension of acceleration. Next physical quantity we will take, that is a force. We know force is equal to mass into acceleration. So here acceleration again can be expressed in terms of velocity per unit time. And again velocity can be expressed in terms of distance per unit time. So final equation will be mass into distance upon time square. Hence here we have a factor, that is m. Distance is nothing but length here, and time is t, that is a t square. So the dimension for this physical quantity will be L1. Mass is present here, so we'll write down m1 also, and t is in the denominator, so we'll write down -2. This is the dimension of force. Now if you want to find out the unit of force, we'll find out from this equation. We know mass can be expressed, the unit of mass, that is a kg, kilograms, distance is in meter, and then time is in the second. So here we have a second square. So this is the unit, that is kg meter per second square is a unit of force, and the dimension is in square bracket L1 m1 t -2. Next physical quantity we will take, that is a pressure. We know pressure is force upon area. Now force can be expressed in terms of mass into acceleration. And here upon area. So we'll write down here mass. Acceleration again we will express in terms of velocity per unit time. And then we have an area. Again, velocity can be expressed in terms of distance per unit time. So finally, we will write down this equation: mass into velocity, that is distance per unit time, means here distance upon time square, and area is nothing but length into breadth, means here we will write down length into breadth. So finally, mass, that is m, distance we will express in L, and time we will express in T, that is T square here. Length and breadth both can be expressed in terms of L, so we'll write down here L square. So finally we will have here, this L will get cancelled. So here we have m upon L into T square. So the dimension of pressure is, L is in the denominator, so we'll write down L minus 1. Power of m will be 1 here, and T again is in the denominator, so we'll write down T raised to minus 2. So this is the dimension of pressure. If you want to find out the unit, we will come to this equation. For the unit, we'll write down, this is kg. Mass will express in terms of kg. Per unit, length, that is meter, and second square. So this is the unit of pressure. Next physical quantity is the impulse. We know impulse is force into time. Force can be expressed in terms of mass into acceleration. Into time. Again, here acceleration can be expressed in terms of velocity per unit time. Into time. In this equation, time factor is getting cancelled. Now here, this equation can be written as mass into velocity. Velocity is again displacement or distance per unit time. Hence, here we have a quantity mass that can be expressed in terms of m. Then we have a distance, that is L, and then time. Hence, the dimension of impulse can be written as L1, M1, T is in the denominator, so we'll write down T minus 1. If you want to find out unit of impulse, we can find out from the above equation. For unit, m, that is a mass, can be expressed in terms of kilograms. Length can be expressed in terms of meter. Hence, the dimensions of impulse is L1, M1 and T minus 1. If you want to find out the units of impulse, we can find out from the above equation. Here m can be expressed in terms of kg. So here we have a kg, length is in meter and then time is in the second. So unit for impulse is kg meter per second. Next physical quantity is a work. We know work is force into displacement. Force can be expressed is equal to mass into acceleration. Into displacement. Here we know acceleration can be expressed in terms of velocity per unit time. So here we will write down mass, acceleration is velocity per unit time into displacement. So here we will write mass into velocity per unit time into displacement. We know velocity also can be expressed in terms of distance per unit time. So directly we will write down here mass into distance per unit time. So we'll write down here distance per unit time, and this time is also there, so time square, into displacement. Displacement is nothing but distance, so we'll write down here distance. Now here we have a terms, that is m for mass, then here we have a 2 time distance, means what, L square upon T square. Hence the dimension for this quantity will be L square m1 T minus 2. And if we want to find out units for this, we will write down unit from this formula. Here we have a m. M is nothing but mass. So unit for mass is kg. Unit for length is meter. So here length square, so meter square upon T square means second square. Next physical quantity will be kinetic energy. We know kinetic energy is equal to half mv square, that is half mass into velocity square. We can express velocity in terms of distance per unit time. So here we will directly write half m distance per unit time square, whole square. Now we will write down here half m. Now distance is nothing but length, so length square upon time square. So we'll write down here length upon time, its square. So finally half is a constant quantity, so it doesn't have a unit. So here we'll write down m L square upon T square. So if you want to write down the dimensions, we will write down dimensions L square m1, T is in the denominator, so we'll write down T minus 2 square. And if you want to write down the units will be, the unit of mass is kg. Unit of length is meter. Here we have a length square, means meter square, upon T square, that is second square. So the unit of kinetic energy is kg meter square per second square, and the dimension of kinetic energy is L2 m1 T minus 2. Next physical quantity we will take, that is a potential energy. We know potential energy is mgh, that is mass, g, and h is a height. Here m stands for mass, g is a acceleration due to gravity, and h is a height. So we'll write down here mass stands for m, then g is acceleration due to gravity, so we'll write down here velocity per unit time, and height is nothing but it's a length, so we'll write down here length or height also, no problem. Now here velocity can be expressed in terms of distance per unit time, so this formula will become m distance per unit time velocity, means here we'll write down distance per unit time, means again here we'll write down time square, and this height can be expressed in terms of length. So here we will write down m for mass, distance and length both are the same quantity, so we'll write down here L square, and for time we'll write down T square. The dimension for potential energy will be L2 m1, T is in the denominator, so we'll write down T minus 2 square. If you want to write down unit for potential energy, we can derive it from this equation. So here m is nothing but mass, so unit of mass is kg, Length, unit of length is meter. So here we'll write down meter square. And unit of time is seconds. So here we'll write down second square. So in this way we can find out the unit and dimension for the potential energy. Next physical quantity we will take, that is a momentum. We know momentum is mass into velocity. Now we know velocity is again distance per unit time. So we'll write down here mass into distance per unit time. So if you want to express this in the physical quantity, we will write down here m for the mass, then distance is L and time is t. Hence, dimensions of momentum can be written as L1, m1, t is in the denominator, so this is -1. And if you want to write down the units of momentum, from this equation, we can write down units from momentum. So m is nothing but mass, that is kg. Length is meter and t is seconds. So in this way we can find out units as well as dimension of a momentum. Next physical quantity we will take, that is a power. We know power is work upon time. Work can be expressed in terms of force into displacement. And here we have a time. Now, force again can be expressed in terms of mass into acceleration, into displacement. Upon time. Now, acceleration again can be expressed in terms of velocity per unit time. So here we have a mass into velocity per unit time, into displacement, that is nothing but length. Upon time. Here velocity is distance per unit time. So directly here we can write down mass into distance. Distance and displacement both can be expressed in terms of length. So here we will write down mass into length square upon t square. Hence, we can express this mass in terms of m, L, that is a length, and t. Hence, the dimension of power can be written as L2, m1, t is in the denominator, so we'll write down t minus 2. This is the dimension of power. Suppose we want to find out unit, so we can find out unit from this formula. So m is nothing but kg. Mass can be expressed in terms of kilograms, so it is kg. Then we have L square means meter square upon t square means second square. So unit of power is kg meter square per second square, and the dimension of power is L2 m1 t minus 2. Next physical quantity we will take, that is a frequency. We know frequency is 1 upon time. Time can be expressed in terms of t, so we'll write down 1 upon t. Hence, the dimension of frequency is, here length and mass, both the terms are absent. So here we'll write down L0, M0. T is in the denominator, so here we'll write T minus 1. This is the dimension of frequency. If you want to find out the unit of frequency, we can find out from this formula. From this formula, we can write down 1 by second, or here we can write down second inverse per second. It's a unit of frequency. Next physical quantity we will take, that is a wavelength. We know wavelength is nothing but it is a length of one wave. So length we will express in terms of L. So here only one quantity is present, that is a L. Hence the dimension of this physical quantity wavelength is L1. Mass and time both are absent, so m0 or m0, t0. And if you want to write down the unit of wavelength, we can write down from this, that is a meter. Next physical quantity we will take, that is a trace. Trace is nothing but force per unit area. We can express force in terms of mass into acceleration. Area in terms of A, that is capital A for the area. Then again we have a acceleration. Acceleration can be expressed in terms of velocity per unit time. So here we will write down m, velocity per unit time, upon area. Now here we will write down mass. Velocity can be expressed in terms of distance per unit time. So here we will write down distance per unit time. Time is also there, so t square upon area A. So if you want to express these terms in terms of the fundamental quantity, we will write down here m, this is for the mass, distance means L, upon t square, area. Area is nothing but length into breadth, so we will write down here L square. Here L will get cancelled. So finally here we have, so dimensions are here. We can consider L minus 1 because here in previous equation L is in the denominator. So here L minus 1, M1 and T minus 2. These are the dimensions of trace. Next physical quantity we will take, that is a strain. We know strain is change in dimension upon original dimension. To explain strain, we can take example of a length. For example, we'll write length. So strain is here, we will consider change in length upon original length. Now in this case, here we have in denominator as well as in numerator, we have same quantity. So it is a ratio of same quantity. So and whenever there is a ratio of same quantity, there is no unit. Hence, strain doesn't have any unit and dimensions. No unit because it's a ratio of same quantity. Thank you friends for watching this video. Stay tuned with Ekeeda and please subscribe Ekeeda. Thank you.